So good morning or good afternoon, and depending on where you are. So first, I wanted to thank the organizers for inviting me to give this talk, which is going to be about observations of isotopic ratios in protoplanetary disks. So the reason we care about isotopic ratios is because they're very useful tools to study the origin of the material in our solar system and also in other environments. So we know planets are forming in protoplanetary disks, but it's currently unclear whether the organics that were incorporated into the planets are mainly inherited from the parent cold molecular cloud, or if they are the result of a substantial chemical reprocessing within the disk phase. So to investigate this, we can measure isotopic ratios in molecular clouds, protostars, and also we can also do this in disks and trace how these isotopic ratios are changing within the evolution of star and planet formation. So contrary to the dust emission in disks, it's not that easy to map molecular lines in disks, in particular the lines that are not so bright from less abundant isotope logs. But fortunately now with ALMA and the great sensitivity, we have been able to detect several isotope logs in many disks. So some of the ratios that we can use right now that we measure in disks, it's first the deuteration of course. So DCO plus and DCN have been detected in several disks, for example, in this work by Jane Wang in 2017. Also, N2B plus has been detected in a couple of disks, and very recently C2D was detected in one disk thanks to a line survey that Ryan Loomis published this year. So fractionation, well, in general, for deuteration, we find that the other disks enrich in deuterium. So there is a very high values of deuteration when you measure DCN over HCN and DCO plus over HCO plus, for example. So when we look at other fractionation ratios, for example, in carbon and oxygen, it's a little bit more difficult to measure. So there have been several isotope logs of CO detected in disks, including the very rare 13C17O by Alice Booth last year. But unfortunately, CO is present everywhere in the disk, so it's very hard to actually measure differences between the abundance of these isotope logs. So the other fractionation ratio that we can measure, it's in nitrogen, in particular HCN and CN. This is the molecules that I will focus for the rest of the talk. So HCN is quite interesting for different reasons, just because it's a small organic, and it's actually believed to be the starting point of the series of reactions that led to the formation of RNA and proteins, for example. So it has a very important biological meaning. But also, and more importantly for us when we observe disks, is that it's actually quite bright. So this is good, which means that we can observe it in many, many disks. And this is just an example of a survey from 2019 by Jenny Bergner, where she observed HCN in a sample of 14 protoplanetary disks of different ages and structures, etc. So we can measure the fractionation ratio in HCN in particular because it's easy to detect, just because it's bright in disks. But before that, let me just briefly mention what fractionation ratios we measure in our solar system in nitrogen. So what we find is that this ratio varies dramatically across different solar system bodies. So this is a figure from a review of Fury and Marty in 2015. So when you look, for example, at the sun, we find that it's highly depleted in nitrogen, in 50 nitrogen. And the value on Earth is about 272. And this is, of course, measuring the ratio between the main isotope log, HCN, abundance isotope log in 15N. In this case, for Earth, actually, it's measured in N2. When you look at comets, you find that they are more enriched in 15N, and actually all of the comets where they have measured the isotopic ratio, they present very similar values, all around 150. So it's not clear what is causing this large variation in our solar system, but it's possible that we are looking at different nitrogen reservoirs, for example, N2 versus ammonia versus HCN, etc. So in disks, what we have been able to detect is actually first the HC15N. We detected these lines of this molecule in 2015 towards the disk around the Herbig star MWC480, which is the one shown here. And soon later, we published a paper with a survey of H13CN and HC15N in a sample of 6 disks that had very different physical conditions. For example, they include Titori versus Herbig A stars, as well as full and transition disks. So we detected HC15N in all of them, except in one disk that it's ion loop. And this is a very cold and massive disk. And actually, it's also very faint in HCN. So it was expected that we wouldn't see HC15N. So here are the resulting disk average fractionization ratios that we measured for these disks. Is that they all have very similar fractionization levels, and these levels are actually pretty similar to what you find in comets, all around between 100 and 200. So these results are consistent with the inheritance scenario for the origins of the organics in our solar system. However, we cannot really rule out the possibility of chemical reprocessing in the disk, and this would change, for example, the profile of the fractionization ratio that we see as a function of radius in the disk. So what are the different weights leading to fractionization in disks? Here I have a cartoon of a disk, right? You have colder temperatures in the midplane, where you have a lot of ices, and then in the atmospheres you have more of a PDR chemistry. So first, everything could be just inherited from the molecular cloud, the parent molecular cloud. Also, we have fractionation reactions that are important in the cold gas that could enrich HCN in 15N. And finally, there is also another mechanism that it's a selective photodissociation that will preferentially dissociate the lower abundance isotopologues of 15N2 instead of the main isotopologue N2. This in the presence, of course, of UV photons, so more in the inner disk and in the surface layers of the disk. So the resultant file that we observe, and these pathways is dominating in disks. So if the inheritance is dominating, then you could expect to see a flat fractionization ratio as a function of radius. If the cold pathway dominates, then we could expect to see a decreasing profile as a function of radius. And then if isotope selective photodissociation is the dominant one, then you could expect to see the opposite, so an increasing fractionization profile as a function of radius. So of course, for this, we need to see what the observation is telling us. And from this survey that we published in 2017, we only had one disk that had that was bright enough to try to measure a profile. The resolutions was not great also. So it's the disk around the Titori star V4046-. So this is a Titori star. It's a transition disk. You can see the cavity that you have in the millimeter dust emission. And here you have the profile that we found for this source. And indeed, we saw a tentative increasing profile of the fractionization ratio as a function of radius, but our beam was a bit large, so we only mentioned that it was a tentative one and should be confirmed. So we asked for high resolution data, and these are the new observations that we have for the 3 isotopologues of HCN in band 7, actually. So it's the J423. And we can really now to start resolving the emission in the disk, and we even see the hole in the center that it's due to the central cavity that we see in the dust continuum. The resolution of these observations now is much better and corresponds to about 15 AU. In the spatial resolution. So this data is actually quite beautiful, and we are actually able to see the hyperfine structure of HCN. So people working on molecular clouds will know that HCN has these several hyperfine structures, and when you have enough sensitivity, you are able to see the fainter satellite lines. And this is really important because it allows direct determination of the HCN column density instead of having to go through H13CN, which is what we usually do because HCN is normally optically thick, so it's not tracing the total column density of HCN. So we measured the isotopic ratio profiles for this disk. These are the Coulomb densities that we find for the three isotopologues on the left. And then on the right, the first thing that we did was look at the 12C over 13C ratio. And we found a rather flat profile as a function of radius, which means that the carbon is not very enriched in 13C. Value that is consistent with the ISM value. And this is also very encouraging because it means that we can use H13CN as a tracer of HCN in the future to measure the nitrogen fractionization ratio. And we can do this in disks where HCN is just too optically thick, or we cannot really resolve the hyperfine structure. So when we look at the nitrogen fractionization ratio, which is what you have in the bottom right, we confirm the increasing profile as a function of radius that we were seeing at the lower angular resolution data. And this means that there is an active chemistry at place in the disk that is actually changing the inherited abundances from the parent molecular cloud. Note that all of this, though, was done in the image plane directly from the observations. So to confirm these fractionization levels that we are measuring, we also did an analysis in the UV plane. And this is a work that was done by one of my master's students, Javiera Diaz, at PUC. And what she found is that the best fit to the observed visibilities is indeed an increase in fractionization profile, and where the levels in the inner disk can be even lower than 70. And in the outer disk, we get values closer to what we see in comets of around 150. So when we look now at the disk average fractionization ratios in disks, we find that we can separate these ratios for the inner and the outer disk, and that's what we did. And what we find now is that actually it's the outer disk that has very similar values to what we see in comets, and the inner disk could be even more enriched in 15N than what we previously thought. Of course, this is only one disk, V4046-, and it's a transition disk, so it's not a normal disk, you would think. So it's of course very interesting to try to see what happens in other disks as well. So right now we have one other disk where detailed analysis have been performed. This is in TW Hydra, where the ratio was measured very, very recently by Hilly Blunt in 2019. And they also found an increasing profile with radius, and also found a very flat 12C over 13C that is consistent with the ISM. So very similar to what we are seeing in the 4046-. So it's now two disks where we have this same behavior. What is unexpected, though, is that when you measure the fractionation ratio in CN, this was done previously in 2017, also by Pierre Blunt, they were finding that the fractionization ratio is higher of about 323 for CN compared to what you find when you use HCN. So this suggested that there are two isotopic reservoirs of nitrogen in disks, and it means we really need to be careful which molecule we use to trace these fractionization ratios. However, there's one possible explanation to this difference between CN and HCN, and it's the fact that they could be, the emission that we observe from these molecules could be arising from different places in the disk. So we really need to ask ourselves where is exactly CN and also HCN, of course, coming from in the disk. There was a very detailed study in 2018 by Paolo Casoletti, who studied the chemistry of CN, actually trying to explain why we see these rings of emission in disks. At that time, it was in TW Hydra, but now there are other disks other disks, for example, these two disks in ion loop, where we also start to see these rings of emission. So what Paolo found in his study is that actually rings are a very natural outcome of CN formation when it's formed by vibrationally excited H2. That's what's starting the chemistry. So this is kind of expected. But also what they found is that the Coulomb densities, when you look at them, the height of the Coulomb density, you see that HCN is actually coming from deeper layers compared to CN. And also from an independent analysis that we are doing now with MAPS, which is a large program with ALMA, we're finding that the excitation temperatures of CN are actually higher than the excitation temperatures that we find for HCN. It means that the CN is really coming from layers, higher layers in the disk compared to HCN. So they will be coming from different places. And this could explain why we see different fractionation levels in CN and HCN. So for that, or to test this idea, we are now reanalyzing the data towards TW Hydra. So this is a project from the Rosetta Stone project that it's led by Ilse Leaves. And we have additional lines for HCN and also for CN. So we are doing a more detailed analysis to try to determine where exactly the emission is coming from, what we are actually tracing. In conclusion, here what we're finding is that in these two disks where we have been able to measure the profile of the nitrogen fractionization, we see this increasing profile with radius, which means that selective photodissociation is actually very efficient in setting these ratios in disks. And this has also been found in chemical models. So this is a work by Visera in 2018, where they actually found that isotope fractionation is completely dominating the isotope selective photodissociation is completely dominating the fractionation ratios in HCN and CN. So as a takeaway from this, because my time is running out, the first thing is that we find disk average HCN fractionization levels between 100 and 200 in disks, and these are very consistent to cometary values. We also find increasing fractionization profiles in the two disks where we have made this study so far. And this gradient suggests that selective photodissociation is the dominant fractionization pathway in disks. And finally, we think that CN and HCN might be tracing different layers in disk, which would explain why we find these different fractionation levels. Just to finish, I just wanted to mention that all the disks that I showed before are pretty isolated and don't really have many threats from their surrounding. But we are starting to look disks that are heavily irradiated by nearby massive stars. And in particular, we have this project that is now being led by one of my master's students, where we look at two disks in Orion, and we are starting to detect some simple organics like HCN, formaldehyde, C2H, besides the brightest CO isotopologues, at least in these two disks that are located in the outskirts of the Orion cluster nebula. And with that, thank you for listening to me.